in them. Ionic compounds have ionic bonding. Molecular compounds have what we call covalent bonding. Basic difference, what we talked about in the video, was that in ionic bonding, electrons get transferred from one atom to another. So when we make sodium chloride, sodium loses an electron, become positive. Chlorine gains an electron, become negative. We talked about those independently. But what makes them sodium chloride is once that happens, sodium is now positive, chlorine is now negative. Chlorine has sodium's electron, and so sodium doesn't want to leave. So you have a positive and a negative, and they're attracted to each other. And they just stick together. It's similar to magnets. Positive and negative magnets. You have positive and negative charges, they have attraction. Okay? So in an ionic bond, electrons are completely transferred from one atom to another. In covalent bonds, electrons are shared. So covalent bonds are in molecular compounds, and because they're molecular compounds, there's no metal, and there's no ions involved. So nothing gains an electron, become negative, nothing loses an electron, become positive, and so there isn't that positive-negative attraction to hold them together. So what happens is you have, say, a couple atoms, they're nonmetals, they're close to having a full 8 valence electrons. Neither one of them wants to give away an electron, and so they share electrons. And the important thing here to realize is when two atoms share an electron, they both count it as their own. So if you have two fluorine atoms, they each come with 7. They each need one more. So if fluorine A says to fluorine B, you can share one of my electrons, and fluorine B says to A, you can share one of my electrons, they both start with their 7, and they claim one of the other ones also. And so they both end up with 8. And you'll see that. So essentially, this onion is going to be our electron for now. Okay? So, if I am sodium, and Jonathan is chlorine, I have one onion, and I don't want an onion. Do you like onions? He doesn't dislike onions. So, I don't want it, he kind of wants it, so I'm going to give it to him. Okay? That is now his. He claims it, I do not claim it. Okay? It is mine, I own it, so I don't want to leave, but I don't want to claim it as mine. Now let's say we're both fluorine. This is one of mine, but if I hold it out, he grabs it also, we're both touching it, and so we're both claiming it. And so he started with his own 7, but he's claiming mine also, and he has 8. If, in the other hand, he holds up one of his onions, and I touch that one, then we each have 8. Okay? So that's how our ionic and covalent bonds are going to work. This is where the video left off. We covered the most basic parts. If you didn't watch it, it might be worth going home and watching it, just in case there's something in there that's going to help you. So we said in ionic bonding, metals lose electrons, becoming positive. Nonmetals gain electrons, becoming negative. And so once they both have those charges, you have the attraction. So this is sodium. This is sodium metal. This is chlorine gas. Just like an ogre. So sodium is going to give electrons to the chlorine. When that happens, you now neither have sodium or chlorine gas. You have sodium chloride. Both elements in that compound have our noble gas electron configuration. In ionic compounds, the atoms are very neatly spread out. We saw this, I think, last week. What holds this crystal lattice together is that positive-negative attraction. So in this case, the greens are chlorines, the yellows are sodiums. Now this is a part of a bigger picture, so there should be yellows kind of in each of these. But if that is positive and that is negative, there's attraction. There's attraction between the yellows and all the greens. But also, these are two positives next to each other. So they repel each other. These two negatives repel each other. Those two negatives, they repel each other. What essentially happens is if you've taken physics and you've balanced forces, every atom is getting pushed and pulled from a million different directions at one time, and eventually each atom finds its happy place where it just sits, where all the forces in all the different directions equal out and it's not moving. That's what's holding our crystal in place. In covalent bonds, we don't have that strong positive-negative charge to create attraction. Well, it is still held together by positive and negative charges. It's just here, positive and negatives have to do with the subatomic particles. So this is a covalent bond between two atoms. In the center of each, we have a positive nucleus, and then going around them are the negative electrons. So the negative electrons are attracted to the positive nuclei, and then the positive nuclei are trying to push each other apart. And the negative electrons are also trying to push each other apart. So again, you have positives and negatives, and in the end, they find the balance, and they manage to hold the molecule together. So where sodium chloride forms that really neat crystal structure, carbon dioxide, which has covalent bonds, is molecular, it has the individual molecules that just kind of pack closely. They're not nearly as neat as an ionic compound. So this is sodium solid. The picture of, not sodium, carbon dioxide solid. This is dry ice. It's sublimating, it's turning into gas. So it's going from solid to gas. And what's holding the molecules together is just those positive-negative attractions between the electron and the nuclei. Each individual molecule is hardly attracted to each other at all. We'll talk about the attraction between molecules in another lecture, but that's a long way from now. Each molecule is independent. This CO2 molecule is independent from that one and that one. If we go back to the ionic, that sodium doesn't know whether it belongs to that chlorine, that chlorine, that chlorine, or that chlorine. There is no specific pairing of this sodium and this chlorine. It's just a ratio. Sodium chloride says there's one sodium per one chlorine. So if you have a giant block of sodium chloride, you may have 1 billion of one, 1 billion of the other, but there's no pairs there. In a covalent or molecular compound, you have molecules. That oxygen is with that carbon and that oxygen, and it will stay like that. So we say each molecule is independent. So, we talked about 8 valence electrons. And we also talked about the Lewis dot symbols. And when I brought that up, I said if Lewis gives you heartburn, you can wait because it's not going to get bad for another couple of weeks. Another couple of weeks is today. Okay? So, this is just a taste of what a Lewis dot structure looks like. We're going to learn how to draw them. But it all comes down to what we call the octet rule. And the octet rule means that in a covalent compound, every single atom needs to have 8 valence electrons. 8 valence electrons is what we call an octet. So when you take these atoms and you put them together to make a big molecule, you have to arrange them so that every atom has 8 valence electrons. So we're going to draw valence electrons as dots, just like we did in our symbols. It's just now we're going to have a whole bunch of atoms put together. And we're going to have to arrange the dots around them all so that each one of them has 8. So this is a carbon with 4 fluorines. And the circles represent the electrons that each atom is claiming as their own. So this is a carbon in the middle, and this is its circle. So it's claiming these 4 pairs of electrons. And so that carbon has an octet. Each fluorine has 8 around it also. This fluorine has 3 pairs of its own, and a pair that it's sharing with the carbon. A shared electron pair is a covalent bond. So that is a covalent bond, that is a covalent bond, that's another, and that's another. There are 4 covalent bonds here. This is just a fluorine and a hydrogen. Hydrogen is the only exception to the octet rule. Hydrogen can only have 2 electrons because hydrogen doesn't have a p. There is no 1p. So hydrogen is happy if it can fill 1s. And 1s only holds 2 arrows, so hydrogen can only have 2 dots. So in every Lewis structure you draw, each atom has to have 8, except hydrogen. Hydrogens will have to have 2. So we said the octet rule is that in a molecule, every single atom has to have 8 valence electrons, and those 8 electrons will be in 4 pairs, with no exceptions. When you're doing Lewis structures, there will never be a single electron, which means if they come in pairs, overall you're going to have an even number of electrons. So hydrogen ends up with 2. Helium only has 2, but because helium is a noble gas, it doesn't form bonds, and so we'll never see it in something like this. So this a Lewis dot symbol is what we did. Okay? We put the dots, 1 dot representing each valence electron, around our center atom, and we paired electrons as we needed. Once we got the 5th one, we had to make a pair. 5, 6, 7, 8 made our pairs. Okay? When you're taking elements, atoms, you're putting them into a compound, you need to figure out how many electrons they need to gain in order to get 8. Because these are covalent or molecular compounds, they're all going to be nonmetals. So they're all going to gain. None of them are going to lose electrons here. You need to figure out how many they need to gain, and however many they need to gain, that is how many bonds that atom wants to make. So, start with hydrogen. How many valence electrons does hydrogen start with? 1. And for hydrogen to be happy, how many does it have to have? 2. So how many does it need to gain? 1. If it needs to gain 1, hydrogen will form 1 bond. So when you're drawing these structures, hydrogen can only have 1 bond. There can only be 1 shared pair of electrons. What about chlorine? How many valence electrons does chlorine start with? 7. How many does it want to gain? 1. So chlorine and all of the halogens are going to form 1 bond. On that picture we had carbon and fluorine. Each fluorine shared 1 pair of electrons with that carbon. Oxygen starts with how many valence electrons? 6. So how many does it need to gain? 2. Oxygen will form 2 bonds there.
So would it just be like oxygen and then the bonds that come with carbon bonds?
Yeah,
Right?
bonds.
Bonds that come with it and then...
We'll see. We'll see. The first example will make it a whole lot clearer. So here's nitrogen. How many does nitrogen come with? 5. How many does it need to gain? 3. So how many bonds do you think nitrogen is going to want to form? 3. Carbon starts with how many? How many bonds do you think carbon wants to form? 4. In that structure, we had carbon with bonds between 4 fluorines. So each fluorine formed the one bond that they wanted, and the carbon in the middle formed 4 bonds. Once we start drawing them, you can always come back to this to test, to make sure everything looks right. Once you get it drawn, you can think, how many bonds did each atom want to form, and how many bonds did I make it form? If it matches, then you're probably right. All right. These are steps. I'm not going to read them. They're not going to make any sense if I just go through and read them. Okay, so they're there if you want. We'll go through them when we do our first example. So the first step is to write what we call an atomic skeleton. Okay? The skeleton is just the atoms, just the symbols. We're going to signify each atom by its symbol. We're going to arrange them with no dots whatsoever. Okay? I am never testing you on your ability to write the skeleton. Okay? After you do some of them, it's going to be very clear how to put them together, but you are always welcome to ask me how to write the skeleton. I am testing you on putting the dots in. Okay? So our first example is going to be formaldehyde. So formaldehyde has a carbon in the center, 2 hydrogens, and an oxygen. You can arrange these 3 any way around that carbon you want. This hydrogen could be here, that oxygen could be there, it doesn't matter. Okay, there's no right or wrong as long as you have 2 hydrogens and 1 oxygen around a center carbon. In most cases, the first atom in the formula is going to be your center atom. Hydrogen, oxygen, and halogens will always be on the outside. Okay? What's on the inside will almost always be something carbon, nitrogen, silicon, phosphorus, sulfur, something like that. You'll see the pattern and you'll catch on really quick.
So you said halogens and hydrogen?
Halogens, hydrogen, and oxygen will be on the outside. They'll never be in the middle. So, second step. Sum the valence electrons from each atom. So you want to look at each atom we started with, figure how many valence electrons each one brings, and add them up. That's how many valence electrons we have to work with. So how many does carbon start with? 4. How many does hydrogen start with? 1. So we got 4, 5, 6. We have 2 hydrogens, each one of them brings 1. How many does oxygen start with? 6. So how many do we have total? 12. So we have 12. My suggestion, and I do the same thing, is write that number down. Okay? It's not part of your answer, but that is what you're shooting for. You have 12 dots put around all these atoms to make them all happy. Okay? Third step is place 2 electrons, so a pair. You're always going to put down pairs. You're never going to put single electrons between each pair of bonded atoms. Each pair of electrons between atoms is a single bond. Okay? So that's a single bond, that's a single bond, that's a single bond. The first ones you put in are like the glue. They hold the skeleton together. Then you can go back and try to make everybody happy. But you have to put the glue in to hold everything together. So I put those pairs in. Number 4 says add remaining electrons to complete the octets. We're going to do it on the outside atoms first. Okay? So I've used 6. I have 12, so I have 6 left. I'm going to start with hydrogen. Do I need to add any electrons to hydrogen to make it happy? No. No, it already has 2. So that's happy, and that's happy. Is oxygen happy? No. No. How many does it want? It wants to gain 6, because it wants 8 total, and it has 2. So I am going to make oxygen happy. I just used up all of my electrons, though. I have no more to move around. Is every atom in this molecule happy? No. Why not? Carbon only has 6. Everything has to have 8 unless it's hydrogen, then it has to have 2.
So it's going to take 2 from oxygen?
It's not going to take 2, it's going to share 2. So we move down to number 5. Now that we've put all of our electrons on the outside and we run out, if we have to get more on the inside, we shift from the outside in. So these hydrogen have nothing else to shift, and so carbon can't share any more with hydrogen. Oxygen has these though. So I'm going to take a pair. It doesn't matter which pair you steal. I'm going to take this one. I'm going to move it there. When I redraw it, I get that. This is a double bond. There's 2 pairs of electrons between the carbon and the oxygen. They're now double bonded. Yes?
Is it always drawn like that, double bonds?
A double bond is 2 pairs of dots.
Okay.
Yeah. If in the past you may have done, instead of single pairs and double pairs, you might have seen lines.
Yeah.
That's fine also. If you're comfortable doing that, I won't mark it wrong. Just in my mind, the dots are easier because you can count and make sure you have 12.
Don't the bonds have something to do with pushing them down, too?
We'll get there. So now, that hydrogen has 2, that hydrogen has 2, that oxygen still has 8. Even though it's now sharing an extra 2 with carbon, it still claims all 8. That oxygen has 2, 4, 6, 8, and the carbon also has 8. Even though it shares every single one of them, it is still happy, because it has 8. So carbon and oxygen have 8, the hydrogens have 2. Everything's happy in terms of electrons. Hydrogen wanted to form 1 bond. How many bonds did it form? 1. So both of them are happy with bonds. Oxygen likes to form how many bonds? How many does it need to gain? 2. It comes with 6. It needs to gain 2. It needs to form 2 bonds. It formed 1 double bond. That counts as 2. So oxygen can either make 1 double bond or 2 single bonds. Carbon comes with 4. It needs to gain 4. So it wants to make 4 bonds. It has 2 singles and a double. So it has 4 bonds. So everything is happy. That is the correct Lewis structure for formaldehyde. You don't have to draw the circles. From here on out, I won't draw them.
That's a good way to check yourself to make sure that you have the right amount,
Right. So if you draw the circle, you're forcing yourself to say which electrons belong to that atom. So you can count. So there's step by step what we did. Now we're going to do hydrogen cyanide, HCN. This one, the skeleton is just how it's written. We have HCN. How many valence electrons does hydrogen come with? 1. How many does carbon come with? 4. So now we're at 5. How many does nitrogen come with? 5. So we have 10 total. First step is to put in the glue. There's my first 4. Yes? The carbon needs to be in the middle. I could have put the nitrogen either here or here though. That's perfectly fine. So I put my first 2 pairs in. The second step, the next step, was to put electrons on the outside to make the outside atoms happy. Is hydrogen happy? Yes. So I'm going to move over to nitrogen. Is nitrogen happy? No. How many more does it need to be happy? 3 pairs, right? So I'm going to put 3 pairs there. There's 8 electrons, and there's 10. I've used all of my electrons. Is everything happy there? No. Carbon is not. How many electrons does carbon have? 4. How many does it need? 8. So, it can't take any more from hydrogen, so it's going to have to come over from nitrogen. If I move a pair over, I now have that. Is that correct? No. Carbon now has 6, but it doesn't have 8. So it's going to share another pair. Like that. We have a triple bond. You can have triple bonds, there are no quadruple bonds. So you have single, double, or triple bonds. This is correct. That's a hyphen. Electrons are fine. Hydrogen has 1 bond. Carbon has 1, 2, 3, 4 bonds. Nitrogen has 1, 2, 3 bonds, which is how many you would predict it to have. So everything looks correct. That is the Lewis structure for hydrogen cyanide. I look at these as like a puzzle. Okay? You write it out, you know what it's supposed to look like, you got the cover of the puzzle, so you know the skeleton. It's just fitting the dots in to make everything fit. And the more you do in practice, the quicker it'll get. This isn't really all that hard. Okay? Practice will help you. So let's do a couple more. We've got carbon dioxide and sulfur dioxide. We'll start with carbon dioxide. How many total valence electrons are in carbon dioxide? How many are in carbon? 4. How many does each oxygen bring? 6. There's 2 oxygens, so that's 12. Plus 4 from carbon is 16. So I've got 16 total. CO2, like I said, oxygen is almost always on the outside, so I'm going to put the carbon in the middle, 2 oxygens on the sides. But remember, you can always ask me and I will tell you this part. So we've got 16. What's my first step?
Glue.
The glue. Hold them together. Now what comes after the glue?
Outside.
The outside. Is oxygen happy? No. So I've used 4. So there's 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I have no more dots. What do I have to do? I have to shift in. I have a couple of choices though. I can shift 1 from either side, or shift 2 from 1, and none from the other. Which one do you think is correct? 1 from each. How do you know? Other than it just looks right. If I moved 2, how many bonds would be here? It would be a triple bond, right? How many bonds does oxygen like to form? It needs to gain 2. So it wants to form 2 bonds. So if I do this, this oxygen's formed 3, that one's formed 1. Neither one of them is happy. If I move 1 pair from each, what I now have is a carbon double bonded to 2 oxygens. Oxygen's got 8, oxygen has 8, carbon has 8. Oxygen has 2 bonds, carbon has 4 bonds.
Why does oxygen like to form 2 bonds?
It started with 8 valence electrons, right?
Right.
So it needs to gain 2 to get to 8.
Right.
And every time it shares 1 to get closer to 8, it forms a bond.
Okay.
So it's going to gain 2, which means it needs to form 2 bonds.
Okay.
In this double bond here, 2 of them came from carbon, 2 of them came from the original. Now we'll do SO2. SO2 looks very similar to carbon CO2, but we're actually going to see it is different. So that's SO2. How many valence electrons do I have total? I have 12 from the oxygens, plus 6. So I have 18 this time. Here's my glue. What comes after the glue? Outside. That's 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I filled the outside. I still have 2 extra left though. So now I can take those extra 2 and put them on the sulfur in the middle. Is everybody happy? No. Who's not? Sulfur. Sulfur only has 6. What do you think we can do? Make a double bond. SO2 is one where you're not going to be able to satisfy all of the rules. Not everyone is going to be completely happy. If I make a double bond, I get that. What is not 100% seemingly correct about that? This is the best we can do, but what jumps out is not being right.
Oxygen. Oh, yeah.
What about it? It only made 1 bond. It wants to make 2. That one made 2. That one only made 1. Why can't that one? Why can't that one also make 2 bonds?
Because then sulfur will have too many.
Then sulfur would have too many. If this pair came over here, sulfur would have 10.
So does it make it kind of unstable?
A little bit. We're not going to cover this, but what happens is you get something called resonant structures, because that one could have a double bond, or that one could have a double bond. In so reality, it actually flips back and forth, almost imperceivably fast. Okay, but then we're not doing that. You just need to pick one and draw it. So the octet rule has to be observed. If something does not have an octet, that is not correct. But if in order to get an octet, one of them has the wrong number of bonds, that's okay. It's better to have octet and the right number of bonds, but in this case, it is impossible to do that. But you have to make the octet. There's no way around that. Okay. So, the Lewis structures you'll be asked to draw, we will have a center atom and then things going around the outside. The only exceptions are these 3. Okay? These have 2 center atoms. So in this case, we have carbon, carbon, C2H6. Each carbon has 6 hydrogens. How many valence electrons does each carbon start with? 4. So there's 8, 9, 10, 11, 12, 13, 14. I'm going to put in my glue. There's 8, 9, 10, 11, 12, 13, 14. I'm out of electrons. Do I have to do anything? No, it's actually already correct. Each hydrogen has 1 pair. Each carbon has 4. Everybody's happy. So that is C2H4. Now we're going to, sorry, that's C2H6. Now we're going to take away 2 hydrogens. So I'm going to erase 2 hydrogens. And now we have only 12 electrons. When we got rid of two hydrogens, we got to get rid of the 2 electrons that they came with. Now we have 12. I have currently drawn 2, 4, 6, 8, 10. I have 2 electrons that I can play with. Where can I put them that's going to make everybody happy? A double bond. Yes. You put it there. Hydrogens each have 1 pair. Each carbon has 8. So that is C2H4. There's a double bond and then 2 single bonds. Now we'll come down to C2H2. I'll erase 2 more hydrogens. We get rid of 2 hydrogens, we have to get rid of 2 electrons. Now I have 10. I've got 2, 4, 6, 8 electrons up here. Now I've got 2 more to put down. Where can I put them? Triple bond. So as you go from C2H6 to C2H4 to C2H2, all you do is you get rid of 2 hydrogens and you add a bond in the middle. So that's a single bond between the carbons, double bond between the carbons, triple bond between the carbons. You'll see questions about these 3, but those are the only ones, like I said, that'll have multiple center atoms. Everything else will be 1 atom in the middle and then up to 4 going around the outside. Okay. So, we're going to take this and we're going to build on it. We're going to get more and more complicated. Okay? When we're drawing up here, it's 2-dimensional. But in the real world, molecules are 3-dimensional. In the taste and smell of molecules, how our brain perceives them is based on their shape. For taste, our taste buds have little grooves in them, and if something fits in that groove, because it has the right shape, our brain senses a certain taste. So our taste buds have a groove that is for sweet. Sugar fits in that groove. Artificial sweeteners, like NutraSweet and Splenda, are not sugar, but they fit in that groove. So when they fit in that groove, your brain can't tell the difference. Smell, the same thing goes on with your olfactory senses. Okay? When I was an undergraduate, I worked at a chemical company, and I made cosmetic emulsions, which are basically lotions. We were primarily sunscreen, but I also made makeup and kind of perfume scents, things like that. Okay? One time we got a job from a company in Asia saying, we want you to make an emulsion with this scent, limonene. And that's the name of the molecule, limonene. And my boss tells me to order it. So I go online and I order it, and it comes in, and I open it, and it smells horrible. Absolutely horrible. So I take it to my boss, and I say, I don't think this is what we were supposed to order. And he said, he looks up the email, and it says limonene, and the bottle I have says limonene. So he says, it must be right, go with it. I mean, we're Americans, different cultures want things to smell differently. So I make it, smells up the entire hallway when I'm making it. I send it over there, and my boss gets an email back saying, what is this? This is horrible. Who would want to smell like this? And he says, this is limonene. This is what you asked for. And they say, well, did you order D-limonene or L-limonene? And my boss, who was, keeping in mind, making sunscreens, was a theoretical physicist. He had no idea what he was doing. I was an undergraduate. I had no idea what I was doing. So we said, what do you mean D or L? I don't know what that means. Imagine this is in 3 dimensions. A D-limonene has this bond sticking this way. L-limonene has it sticking that way. One of them smells like wet dog. The other one smells pleasant. So that is what was going on. That is the difference in taste. One bond pointing this way versus that way makes that big of a difference. So we're going to have to predict what shape our molecules have, okay? Everything in our body that does something, the molecules in our body that do something are proteins. They're called enzymes. And they have a very, very, very specific shape. There are hundreds of amino acids in that protein. If one of them is pointing the wrong direction, that enzyme will not function. Okay? If you take a drug, a lot of drugs that you take are a specific shape. If one bond is pointing the wrong direction, it will not work at all. That's how important this stuff is. So we're going to predict the shape of our molecules using our Lewis structure. We do it using what we call valence shell electron pair repulsion theory, VSEPR. People tend to call it VESPR. Okay? Yes, I know the S is before the E, but try saying VSEPR. It just doesn't sound as nice as a VESPR. The whole thing is based on the fact that you have these electrons out here. They're all negative. If they're all negative, they're repelling each other. And so these atoms will move in such a way to get the electrons as far away from each other as possible. These valence electrons want to stay opposite of each other if possible. So, when we talk about shapes, there's going to be 3 steps. We're going to draw the Lewis structure. Then we're going to figure out what we call the parent structure. To find the parent structure, we're going to count the number of things around our center atom. And a thing is a non-bonded electron pair. So with our sulfur dioxide, that is a non-bonded electron pair. That is what we call a lone pair. It's on that sulfur. It is a thing, but it is not part of a bond. A single, a double, or a triple bond all count as one thing. That's a thing, and that's a thing. So how many things would you say are on the sulfur? 3. 1, 2, 3. A bond, whether it's single, double, or triple, is a and a lone pair is also a thing. It's not on camera, don't worry. That is on camera. So the sulfur has 3 things. A double bond, a single bond, and a lone pair. Okay, so I'm going to keep referring to these things and asking you how many they have. So these things want to get as far away from each other as possible. We're going to come back to our onion. And this is now going to be our center atom. Okay? So we're never going to have just one thing. You're going to have 2, 3, or 4. So if I take 2 things and I put them opposite each other so that they're as far away apart of each other as possible, where am I going to put the second one? I normally bring toothpicks. I forgot my toothpicks.
Hope you don't plan on eating onion.
If you have 2 things, it's very easy to get them as far away from each other as possible, right? Just straight opposite of each other. We get to 3 things. How do you think I can put 3 things in this onion and keep them as far away from each other as possible? Like a triangle, or a peace sign, or a Mercedes-Benz symbol, or whatever you want to call it. Those 3 things are as far away from each other as possible. Okay? 3 is also easy to see. The hard one is 4. And I'm telling you it's hard And so it's not what you're thinking probably. Where do you think I can do with 4? I got to put this one in.
Maybe like in
Like that, but this is in 3 dimensions. So I can take these and point them down a little bit. Like that. That is 4 things. It is not just a cross shape. In 2 dimensions, yes, that's as far away from each other as possible. But in 3 dimensions, it's this. It's like a pyramid with one sticking straight up. Everybody see that?
But what's causing the 3 lower ones to shift downward?
This one.
Okay.
If they were straight, flat, like they were before, they're closer to that one than they have to be. And so if this was a real molecular model and it was correct, no matter how I turned it,
it would always look
the same.
Okay. Okay.
And so I think in lab this week we make, I think that's this week that we make models. You'll have models and you'll actually see it. But not onions. You save the expensive stuff for lecture. So this is what they look like. 2 is opposite each other. 3 is like a triangle. And then the 4 is that shape. So this is methane, CH4. Carbon in the middle, 4 hydrogens. How many things are around that carbon? 4. There's 4 single bonds around that carbon. So it goes like that. It's that pyramid shape with the one sticking out the top. Mathematically, there's no way you can look at that and figure out those angles. So you're going to have to memorize, in that shape, that angle is 109.5 degrees. If I have 2, what do you think is the angle between them? 180. 360 all the way around, that's half of it. So 360 divided by 2 is 180. What if I have 3? What do you think the bond angle is? 120. 360 divided by 3 is 120. Each one is 120. So those, if you don't remember, you can figure them out on an exam. I would not suggest trying to figure out 109.5. So these are what we call our 3 parent structures. We have linear with 2, trigonal planar with 3, and tetrahedral with 4. Yes, do you need to know the names? Yes, do you need to know the angles? So if you have 2 things, is linear, 180. 3 is trigonal planar, 120. 4 is tetrahedral, 109.5. This planar means they're in the same plane. So it's 2 dimensions, they're all on the same plane. Okay? These are the only 3 parent structures. What you're thinking of are the molecular shapes. Yes, there are more.
Lucky us.
Yes. In order to find the number of things, you have to draw the Lewis structure. You're never ever going to want to draw a VSEPR structure shape without doing the Lewis structure first. Okay? So I have SO2 already drawn here. So we're going to do number 3 as our example because we're running a little short on time. So, SO3 is here. How many things does it have around the S? 3. If it's 3 things, what is the parent structure? Trigonal planar. 3 things is trigonal planar. Trigonal planar is 120 degrees. How many? Oh, that doesn't work. CO2 is that. How many things are on our carbon? 2. That double bonds, that double bonds. So what is the parent structure of CO2? The one that has 2 things is linear. It's 180 degrees. Once we know the Lewis structure and the parent structure, we can draw what we call the molecular shape, or the VSEPR shape, or the VSEPR structure, or something along those lines. Okay? What you're going to do is you're going to draw your best attempt at a 3-dimensional molecule, including the lone pairs, and then you're going to erase the lone pairs, and whatever is left is going to be the molecular shape. So this is water. H2O, if you do the Lewis dot structure, the oxygen in the middle also has 2 lone pairs. So the oxygen has 2 bonds and 2 lone pairs. That's 4 things. It's a tetrahedral parent structure. And so this is the best attempt at drawing that pyramid thing with 1 going up. Okay? 2 of the things are hydrogens, and 2 of them are lone pairs. So you'll draw this, and then erase the lone pairs. These are the instructions for writing thing. We'll do an example so you can see. What she was getting at was the molecular shape list. Every parent structure has molecular shapes that are possible to come from it. It depends on how many lone pairs you erase. Okay? So, if you have something with the formula A, where A is your center atom, and then 2 things around it, so AX2 is the generic formula, there are 2 things, and they are both atoms. Because you can never have a linear with a lone pair, that will never happen. Linear is always linear. There's nothing you can change there. Okay? But if we have a formula like this, where there's 3 things, we can have 3 bonds like that, or we can have 2 bonds and a lone pair, like we had with our SO2. If you erase nothing, your shape name is the same as your parent structure name. So parent structure here, because there are 3, is trigonal planar. We erase nothing, so the shape is trigonal planar. If we erase 1, we get bent, because it looks bent. Once you erase the lone pair, what you have is X, A, X, and it's bent. If you start with 4 things, the tetrahedral parent structure, if all 4 are atoms, your shape is tetrahedral. If you erase 1, 1 is a lone pair, you get what's called trigonal pyramidal. So trigonal planar with this, where they are all in the same plane. If we go back to our pyramid, let's start crying. Onion juice, who knew? If we start with that, but we erase our lone pair, we now have just the pyramid part. So this is trigonal pyramidal. Yes?
Can you explain how you, like, count how many there are sometimes?
So counting the number of things.
Yeah.
So remember, the things were a bond or a lone pair.
So you basically just not count the middle part, like A.
Right. You're counting how many things are around the A, is what you're doing. So A is your center. You're counting how many things are around the center. So in all of these cases, there are 4 things. Here there are 4 atoms. Here there are 3 atoms in a lone pair. Here there are 2 atoms in 2 lone pairs. If there are 4 things, it's a tetrahedral parent structure. But the shape depends on how many of those things are lone pairs. If it's none, it's still tetrahedral. If it's 1, it's trigonal pyramidal. And if it's 2, it is also bent again.
And it's kind of hard to see when it's just, like, the letters.
I'll give you so here, example of that is NH3. In NH3, you get that. That's what you start with. There are 4 things, but that one is a lone pair, so I erase that. And so I am here. So this is trigonal pyramidal. The A bond angle is based off of your parent structure.
I thought you said the single bond was so important.
It is. So we started with 4 things. There was 3 single bonds, that's 3 things, and 1 lone pair. So that's 4 things, right. You don't want to draw that as final step.
I thought that was single bond.
You're fine. So we've got 3 single bonds and a lone pair. There's 4 things. We erase the lone pair, we have that. You're going to be asked to draw a structure and label the bond angle. Okay? Bond angle comes from the parent structure. Between now and Thursday, we're going to leave it at that. Okay? The bond angle comes from the parent structure. Bond angles in tetrahedral were 109.5. Bond angles in trigonal planar were 120. Linear was 180. If you want to do the homework between now and Thursday, you're welcome to. Unless you are not going to have time this weekend, my suggestion is to wait until Thursday. We'll finish what was in our lecture. We'll go over some examples, because that's basically what our lab is. And we'll talk about some exceptions to those bond angles. So remember, the homework is that Word document. If we do want to get started, you can just do the first 3 quarters or whatever. Skip the part to have to do with this.
So how much is the next Tuesday, right?
Yes, you have another week.
I thought when it pushes down, it has to do with the type of bond that it is. Whether it's a single bond or a double bond.
Single and double bonds have different lengths. We're not going to get into that. What happens?
I don't know, I just vaguely remember something.
What you're thinking of is you get that. They're 109.5. If you pluck that off, this lone pair here is actually going to push these down a little bit.
Is that what I'm thinking?
That's what you're thinking.
Yeah, okay.
So we'll talk about that on Thursday.
Okay.
And so it's going to be less than 109.5. They get kind of compacted in there. I think that's what you're thinking of.
Probably. And if we don't do good
I like the
on one of
onions.
our tests,
Thank
you
you.
drop one of our test scores, right?
Yes. Hopefully this one is your worst one, and these go up. I think, in terms of odds, very few people unless you missed one, very few people will drop the first